Hello students, welcome back. So in this session, I'm going to be talking about the need for NumPy arrays for numeric computation. Why do you even need NumPy arrays when you can do the same operation using your list? So I'm going to convince you by showing you, by running a little test, an experiment, to show you why you need NumPy array and how NumPy array it shines and it dominates your list. Okay, the first thing you want to do is import these necessary libraries. I'm importing my numpy as np, importing my time. This will allow me to time my process, like how much time it takes to do a certain process. And also importing my get size of. Okay, this will allow me to see the size of my variable. And also importing random that will allow me to generate some random numbers. Okay, so let's compare the size first. Let's start with the size. So I'm creating a list, okay, a list of 100 elements. Okay, this is the way I create a list of 100 elements, and I print my X list. So this is my printing right there. I printed my X list. Then I'm printing the size of my list. Okay, get size of, and as you can see, the size of my list is 856 bytes. And when I create my NumPy array, then I print the size of my NumPy array, and you can see it's 512 bytes. So this seems to me like almost twice. Okay, so your list is all occupying almost twice the space than your NumPy array. Okay, this makes a lot of difference when this size is very big. So if I let me comment this line out so I don't have to keep printing this. Let me make this thing a little bigger. Let's make this thing as 10,000. And if you run this, you're going to see, oh, look at this, 80,056 bytes. This is 40,000. So NumPy is almost half the size of your list. Very important and very helpful. Okay, now let's look at some performance on element-wise addition. So let's say you want to add a number to all elements of a list and NumPy arrays. Let's do that and let's see how much time it takes. So we're going to add a number to all the elements. Okay, we're going to first start with the list and then we're going to do with the NumPy array. Okay, so I'm adding 100 to all elements in a list. So first I create my list. Okay, this creates my list right here. And how many elements are there? 10 million, 10 million elements. Then I actually get my start time, like how at what time my process started. Okay, this tells me the time my process started. This is where all the operation is happening. Okay, so this is saying I create a new list, new list, empty list. Then I'm inside my empty list. I'm taking my old list. I'm iterating over every element of my old list, and I'm adding 100 to that. Okay, and then I'm appending it to my new list. And then when this is done, my for loop is done. Then I check my end time, like at what time the process ended. Then I print my difference. Okay, I'm printing my difference right here. This prints my difference, and then I'm also printing my original list, the first 10 elements of my original list, and I'm also printing the first 10 elements of my new list. So as you can see, it took 1.01 seconds. All right, to do this process for 10 million numbers, it took 1.01 seconds. Okay, so this was the initial number. Now it's 100. 1 plus 100 is 101. 2 plus 100 is 102. So that's what these numbers are. All right, now let's do the same thing on NumPy array. And let's see how NumPy array fares. So come down. All right, I'm going to add 100 to all elements in your NumPy array. Okay, same thing. I'm creating a list, converting into a NumPy array. Okay, and then I'm doing my start. I'm checking my start time. Then this is the way I'm using. Basically, NumPy, you don't actually use a for loop. You just say x new equal to x NumPy plus 100. And look at that. Isn't that a lot easier? Look at this is so easy. And this one you had to use a for loop to go through all this thing, right? If you want to add 100 to every single element, you have to create a for loop. In this case, you don't have to create a for loop. You just say x new equal to x NumPy plus 100. All right, then I check my end time and then I print my difference. And if you look at it, is 0.0625. All right, this is 1.01 second. This is 0.0625. Let's see how fast it was. Let's see how fast it was. So copy this, come over here, paste it. Now, so I'm going to divide 1.01. Okay, 1.01 divided by uh, 0.06. 2, right? 25. This is 0.0625. So I'm dividing this by this number right here. Okay, I'm taking this number, dividing by this number just to see how fast it is. Oh, it's 16 times faster. So your NumPy array, I just showed you, is 16 times faster when you're adding 100 to every single elements of your container. All right, let's do performance test on element-wise squaring. Let's say you have a list of numbers, okay, and you want to square every single number. And let's see how your list does and how does your NumPy array fare in that. So come over here, all right, and paste it over here. So let's square all the elements of a list. Okay, so in this case, this is my number of elements. Okay, x list equal to list. This is I'm creating a list. I'm putting my start timer. Okay, this is basically pretty much the same as the top one, except now I'm appending e to the power 2. Okay, I'm basically taking every element and squaring that element, and then I'm printing my end minus start time. And as you can see, it took me 1.73 seconds. Okay, all right. Now let's do the same thing using NumPy. So we're going to square every single element using NumPy. And let's see how much time that takes. And it took me 0.03125 seconds. Well, how fast was it? Let's see. So how fast? Well, you're going to say 1.7, right? 1.7334, which is this number. 1.734 divided by this number, 0.03125. Okay, so I'm dividing by this number right here. All right, and let's run this and let's see how much time it took. Oh, 55. So NumPy is 55 times faster when you were squaring the numbers. Okay, great. NumPy is shining so far. Now, let's look at the performance on addition of two vectors. So a lot of time you have vectors and you want to add them. So let's do that. So we can simulate vectors in list. Okay, we can simulate a vector using a list right here. So let's say my number of elements is right here. This is my number of elements. Okay, this is my number of elements. So this is my first vector. Okay, this is my list. This is my list 2. So this could be representative of two vectors. And then I'm adding these two lists together. So I'm using list comprehension. So this is a little for loop. It's going to add these two numbers. All right, and then I time it. Okay, I want to see how much time it takes. It took me 1.17 seconds. So I'm adding this vector, okay, this list, and I'm adding the elements of this list to this list right here. All right, and by the way, if you want to see what your result list looks like, you can also print, just type result, okay, result list, and print out, let's say, first 10 elements. All right, and actually, we can just print this out over here. So you can see, and there you go. You can see 0, 2, 4, 6, 8, 10, because you know this is your 0 to this is going to be 0, 1, 2, 3. This is also going to be 0, 1, 2, 3. So when you add these two vectors, this is going to be your answer, 0, 2, 4, 6, 8. Okay, so now let's do the same thing using NumPy array, and let's see how much time it takes for the NumPy array to add two lists or two NumPy arrays. So these are my two vectors, vector 1, vector 2. Okay, I'm using NumPy array to actually create these vectors, and then let's run that and look at that, 0.032 seconds. It was blazingly fast. And how fast? Well, let's find out how fast. Well, this one was 1.17, right? So I'm going to copy, paste over here, divided by, and then 0.03, 0.032. Okay, I'm dividing by this number right here, and run this cell, and that's going to tell you 36. So it's 36 times faster. Great. Now let's do matrix multiplication, because we need a lot of times matrix multiplication. And let's see how fast is your list and how fast is your NumPy. Okay, so I'm creating a 3 by 3, a 300 by 300 square, two basically matrix, a 300 by 300. So this is my 300 by 300 matrix. This is my 300 by 300 matrix. Now I did this experiment before. It took me approximately 8 seconds. Okay, when I did 400, when my number of elements was 400, okay, it took me 18 seconds. So let's go with 8 seconds. All right, so while this is proceeding, I'm going to explain you what's happening. So this is my matrix A right here. This is my matrix A. This is my matrix B. And I'm actually initializing. This is my result matrix. Okay, this is where I'm going to be storing all my result. I'm creating my start timer. This is my end timer when the process ends. This is where all the process is happening. What it's doing is is basically multiplying two matrices. Okay, this is the math, this is the logic that's taking care of that. And then at the end, I print my how much time it took you, or how much time this process took from end to finish, or from start to finish. So end minus start, and the answer came out to be 11.02 seconds, approximately 11.02 seconds. Okay, in your case, again, it could be a little different depending on your speed of your computer. Now, let's do exactly same thing using NumPy array. And let's see how NumPy array fares for the exactly same thing. So this is my NumPy array. Okay, I'm creating a random integer. Basically, size of this matrix is n by n, which is exactly same, right? 300 by 300. All right. This is my matrix B, creating a matrix B of size 300 by 300, and then I'm randomly putting some numbers between 1 comma 11, and then I'm doing exactly the same thing. Now look at this, I'm actually multiplying these two matrices. So this is the way I'm multiplying: A and P at the rate B and P. This is how you multiply in your NumPy, by the way. All right, and let's see how fast it is. Oh, look at that, very fast. Now let's compare that now. How fast? Let's compare that. So you divide 11.02, okay, 11.02, you divide it by 0.078. All right, and let's see how fast it is. Oh, look at that, 141 times fast. That is great. Okay, so I hope this convinces you that why NumPy array is an ideal option and a good option when you want to do numeric computations.